Welcome to an NMR tutorial on the effects of dynamics on the NMR timescale and the conformation of analyte molecules. For all the amazing information NMR gives us, it is both insensitive and slow. The sensitivity we've previously addressed, it results from the small population difference we observe in our spin states due to the magnetic field. But what do I mean when I say slow? Well, the above diagram marks out roughly the timescales over which physical processes occur, and the timescale over which various techniques can report. That's the top and the bottom respectively. So we can see the very fast atto to femtosecond timescale here. There are not very many options for monitoring, but there are important phenomena occurring. So there's vibrations and excited states. As we get down to the picosecond timescale, there are more options available, and some of those include NMR-based techniques, which are shown in these three-dimensional shapes. However, the NMR information we're most interested in is the J coupling and chemical shifts for molecules, and you'll see that they are at the slow end. And they're slower than many processes, including structural changes of our molecules, which are significantly faster. As we mentioned in the last tutorial, this means that the structures we see in NMR are normally averages of multiple conformations. And this is where we touched on this before. Our rotating alkyl chain here has various potential coupling constants depending on the angle. But in reality, it rotates too quickly, and what we see is an average with a J value somewhere around 7. This is only true because it's free to rotate, however. If we locked it, the story would be quite different. Now, I don't think it would be difficult to persuade you that this proton beside the fluorine is quite different from this proton which is beside another proton. But these two protons here are also inequivalent, as are these two here. And this is due to different coupling because of their spatial arrangement. So the fact they're locked in a ring means that these are no longer interchanging. And in fact, it's easier to see in this type of conformation. And even if the molecule was symmetrical, you would find that the protons on the faces are in fact different to one another, and indeed these are different to one another as well. However, these two protons and those two protons are going to be the same, and that is because their spatial relationship to other protons to which they can couple is the same. We'll talk about diastereotopic protons, Rotamers and Atropisomers, and I will even fit in a couple of personal examples. So now for an example to demonstrate the values of J couplings and shape in structural determination. I have no idea if this molecule actually exists. There is one reference for it on SciFinder, and that's a 2010 patent on electrochemical energy storage. That doesn't actually matter because the spectra is simulated. So what can the spectra tell us about the arrangement of our atoms in space? Well, we're going to approximate that this cyclic ether system behaves like a cyclohexane and chair conformation. So here, any of our groups could be in an axial or equatorial position any of these. As you can draw two conformations of your cyclohexyl chair, the up or down you can observe on this flat structure does not tell you anything about whether these are axial or equatorial and how they relate to one another. So the most downfield protons in this structure are going to be the ones that are attached to a carbon bearing two oxygens, so attached to two electronegative groups. I'll go a bit further, information not easily proven, but this signal here, this downfield one, is that proton. We'll come back to that later because I actually want to start here at this other downfield proton. Now, the reason we start there is that there is a large J coupling. And in the context of this ring system, we know then that the only way we get that J coupling is to have an axial-axial relationship between two protons. And this allows us to define the non-hydrogen substituents that are attached. So if we say this is axial, this is axial, then we know that this hydroxyl is equatorial and this methyl is equatorial. So let's look for the next signal. We're looking for a large J coupling doublet and then also a quartet for this methyl group. Now this bond can rotate freely, so we should expect J coupling of around about 7 Hz. And it's easy enough to identify. It's this triplet of quartets here. Now, you might be a bit confused by the fact that it's apparently a triplet. What this is telling us is that we have two very similar couplings and we can't separate them, so we're only seeing one J coupling and it looks like a triplet. That's telling us then that we have an additional axial coupling, which means that this position must also be axial. This is equatorial. Now when it comes to identifying this proton, we know that we have a large axial coupling, and we know that being attached to a carbon with an oxygen, that it should be further downfield than the signal we've just looked at before. So I think it's quite obvious in the system that we're looking at C. So there we have the large J coupling we spoke about. And we also have a smaller J coupling of about 3.5 Hz. And this means that we have either an axial equatorial or equatorial coupling. We've already said we know our proton is axial, so it must be an axial equatorial coupling, and that means this proton is equatorial and this substituent is axial. And actually this fits what we know about how these chair conformations must work, because if this hydroxyl substituent is pointing up, then the next equatorial substituent must point down, and so this position must be axial. We have to identify now this signal, and it must have again a J of around about 7 quartet and a small coupling for its axial equatorial coupling, and we have the same thing as we previously observed. There's a similar coupling that gives us a quartet, and that coupling is to this proton. This is an equatorial coupling, and that means that this is equatorial and that is axial. And so we have defined the positions in space of all our substituents of this chair conformation. Now you might have wondered in the previous slide why it was that we never saw any coupling to the OH protons. And that's because we exchanged these using a hydrogen deuterium shake. And I'm going to now talk about what is an exchangeable proton, what are we talking about when I say that, and when should you expect such protons to occur. Is the exchangeable protons, and some reference to this has been made previously in interpreting signals, and I hope to give you a little bit more detail about what's happening here. So this doesn't mean anything sophisticated. It is literally swapping protons, and in practice it usually refers to hydrogen to hydrogen or hydrogen to deuterium exchange. The important point for hydrogen to deuterium exchange is that D is a spin equals 1 nuclei, and that means that within the range that we are looking at for proton NMR, we are not able to observe a signal. Okay, and these are calculated or literature pKa values. So I want to start with this proton here. Has a reasonably low pKa, and it's possible because of that for this proton to come off and go onto water, and a proton from water to be exchanged onto this oxygen. And that is literally all we are talking about with exchangeable protons. Protons that can exchange with other protons in the same molecule, with impurities, or with the solvent on a time scale quicker than our NMR experiment. I said within the same molecule, and you can see here. This is an example of what that would look like. So these protons are being flipped. And there are some rules of thumb for identifying these. So you're looking for low pKa's, ability to hydrogen bond, and attachment to a heteroatom. These are not necessarily independent of one another. And they are normally broad. This is due to averaging the various exchange states, and they don't display coupling in many cases because the coupled protons are exchanged over the course of the experiment. I should say that we normally treat exchange as a binary proposition, back to why in a moment, but it's just worth bearing in mind that in fact different protons exchange at different rates. The rates vary differently over the pH of your solvent. It can also be concentration, solvent, and purity dependent, and this means that some features like the appearance of coupling are actually quite variable, sometimes even for the same molecule. Now the reason we treat it as binary is that normally our way of confirming the existence of exchangeable protons is simply to add a large quantity of deuterium compared to the small amount of hydrogen we have present and shake. And then the vast majority of the protons that are exchangeable on our molecule will be exchanged to deuterium, which we will not see in this NMR experiment, and the signals will disappear. To give you an idea of what that looks like, here is an antibiotic molecule, and you can see there are a few broad signals. This one you would suspect, due to its breadth and absence of coupling, to be an exchangeable signal. It would make sense for that to be our NH2 here. And this is a bump in our baseline, which may or may not be a signal at all. But we can see after exchanging with D2O that both of these vanish, and we are able to say that those signals were exchangeable protons, and in fact we have our amine and our acid. So I'm going to move on now to the concept of diastereotopic protons. So this is a bit of an extension of the previous discussion, but this time our protons can rotate. So although they are not locked in place, they are still inequivalent. And this might seem odd, especially when you look at this flat molecule here, and I'm telling you that these two protons are not equivalent. But look at the three-dimensional model, and I think this becomes clear. You can see there is a group of the stereocenter here that is orientated onto one face of our molecule. If we look at these two protons, and I ask you to rotate this in your head, I think what you will realize is that it is impossible to have these two protons become exchangeable, to become equivalent to one another. And this is because the two faces of the molecule are different. This means they are inequivalent and they couple, and this coupling is going to be 14 to 17 Hertz. It's a big one. It's the presence of the chiral center which causes this. So you can see if I was to remove that chiral center, you would then have two equivalent faces. And if you then rotate this, these bonds, the protons become equivalent, they invert environment. Now, you don't have to make three-dimensional models to test this. There's actually a very simple test for diastereotopicity. So take your center, I've identified this one here, and replace an atom on it, one of the atoms on your diastereotopic center that are equivalent to one another with another atom. So I've replaced this red hydrogen with a fluorine, and that gives us one state. If we then take that back off, so go back to our original molecule, and instead make the substitution on the other hydrogen, we end up with this molecule. If our protons are diastereotopic, these should be diastereomers of one another. Now, diastereotopicity requires there are two or more symmetry elements after replacing the proton, not that there was one previously. So I'd like to direct you to the example in the box. This molecule has no chiral centers. However, if you replace either of these protons, both the exchange site and the central atom will become chiral. As a result, these protons are actually diastereotopic. The same actually applies to enantiotopic protons, although in most cases this is less important. So this is where a single substitution would make enantiomers. Enantiomers are normally equivalent in our NMR spectra, and so these protons are also normally equivalent. However, in principle, in the presence of chiral molecules, be it a solvent, Lewis acid, whatever, the two sides of my molecule here could again be made inequivalent. And if that happened, I would again essentially have diastereotopic protons, and I would be able to see these enantiotopic protons separately. So they would become inequivalent. So there's a difference between protons that are enantiotopic and therefore can be made inequivalent, and groups which can never be made inequivalent. And that's what I'm demonstrating here. If you can draw an axis of symmetry through the central atom, then your group is homotopic, and these will always be equivalent. Enantiotopic protons, on the other hand, are mirror images of one another. Again, there is no need for these protons to actually be attached to the same center. These protons here are enantiotopic. So from the exchange of protons, let's move on to situations where the only exchange is of the position of one atom in space. This conformational interchange involves the interconversion of two or more conformations. I mentioned earlier that conformational change is fast compared to NMR. This is not always the case. So in this context, we're talking about changes that are close to the NMR timescale. We have an example here. These two methyl groups interconvert. You can see that if there's a rotation around this bond, these should be equivalent. So at room temperature, you do indeed see a single peak showing these can interconvert. However, they're not as fast as they might be in a molecule less prone to rotational problems, and so they're quite broad. So they're still relatively slow. They're approaching the NMR timescale. As you cool this even a little bit, you see the signal broaden as the range of states that are being seen by our NMR experiment increase, until this starts to form two distinct populations. And at this point, we are seeing the protons, the methyl groups on each side as inequivalent, slowly interchanging. As the interchange becomes yet slower, so it isn't affecting what we see on an NMR timescale at all, these peaks become progressively sharper until at -50, they are essentially completely different signals, and they're not broad. And these methyls are now inequivalent. I should say that if you get stuck somewhere in here, it is possible to see pretty much nothing, so the peaks vanish. So that example involves rotation around a bond, but you can also have an inversion around an atom. So if we take an amine with three identical groups, and here we have an arrangement that goes 1, 2, 3. Now we can rotate that easily around this axis here, and we can have 3, 1, 2 and 2, 3, 1. However, rotation can't get us to 2, 1, 3. So if we try and rotate this group one further towards this here, we end up back at 2, 3, 1. So the only way to interconvert these two states is to push through a pyramidal transition inversion, so you end up at this more linear transition state, which is higher in energy and therefore slower. Nevertheless, in the case of amines, it happens pretty fast. So where tri-substituted amines in principle could be chiral, actually they interconvert too quickly. However, if we go down a row in the periodic table, phosphines are much harder to interconvert. In fact, this example is specifically synthesized to do so well. Now I want you to look at H, A, and B on this diagram. This system is too hindered to rotate around here, so these should be inequivalent. The reason they're inequivalent is that we have this phosphorus popping up out of the plane. So this is all one plane, however the two planes are inequivalent because of this phosphorus. However, the interconversion actually happens here, is the phosphorus interconverting between being above the plane and below the plane. So we can see at -50, we can see HA and HB and indeed a number of other signals as being distinct, and as we warm it up and the interconversion of this phosphorus center increases, these signals vanish. HA and HA disappear. They would eventually coalesce and we would see signals reappear if we warmed up enough and the molecule was stable enough to allow that. Now, I've shown you that kind of inversion around the center. For organic chemists, it's actually more common to observe rotational interconversion. So we're back where we started with our simple alkyl chains. Now, where we have different conformations that we can reach by rotation, we have rotamers. So these two, energy high, the two minima with an energy high between them. So these are rotamers of one another. An energy gap is overcome to go from one to another. Now, the timescale for interconversion of these rotamers is proportional to the energy of the molecule, or temperature, and the energy of the barrier to rotation. For most molecules, like our alkyl chain, it's faster than NMR measurement, as we see before. So what we get is an average. However, if it's really hindered, interconversion might be very, very slow. This is a chiral ligand or catalyst known as BINAP, and it can be bought as either pure R or pure S, with the chiral center actually being axial chirality around this axis. And the calculated interconversion temperature for these two is about 500 degrees Celsius. And they come as these powders. What we often end up with is something in between. And a classic example of that is when the interchange is slow enough to see in the NMR, but too fast to give two distinct compounds that you can separate and handle. The reason this is particularly worth knowing about is that at some point you will have a spectra that looks impure, but actually just has NMR timescale atropisomers. And the way to confirm this is by making the peaks change proportions, and that can be done by changing the solvent or the temperature. So here is a literature example. This is a tertiary amide. Such structures often have slow rotation, and rotation is hindered around this axis. And the proton we're observing is this one. So you can see we have a slightly broad signal for this. However, it's still coupling to this proton here. Now they've tried a range of different solvents, and you can think of these interconversions, conformational changes, as being like a chemical reaction in the sense that some solvents will allow it to happen more easily, would be favourable, and others will make it more difficult depending on the interactions between the molecule and the solvent. And here in their less polar media, the chlorobenzene and chloroform, we can see that interconversion is quite slow, and we see separate signals for two different conformational forms. However, for polar aprotic solvents, DMF and DMSO, this interchange is faster, and we see only a single signal. So the way they then check that these signals, they use chlorobenzene as it happens, are in fact rotamers of this form, is that they heat it up from 25 degrees, they see the signals start to disappear as they come to the NMR timescale, and then they cool it down again to make sure that they are not in fact just observing decomposition. And the change in the proportion of these in the shape tells us that this was a conformational effect. I just want to finish off with a personal example. Here there are two sets of geometric isomers on the NMR timescale. There are those generated by the through ring plane of rotation, so that is along here, along this carbon-nitrogen bond. And the readout for that is these diastereotopic protons here. And there is also a plane of rotation through this nitrogen in the other direction, so through the Bock group, and that is the T-butyl group spinning around here. So you can see the two inequivalent diastereotopic protons. This is the room temperature NMR. These are quite nicely defined. They're completely inequivalent to one another. The rotation around this axis is slow. However, these signals are broad, and these signals are the result of the rotamer around the Bock group. Now I want to draw your attention to two things in particular. Firstly, the easiest way of seeing this is the Bock group here, because it should be a single peak, and it's not. So you get two peaks here. The second is that these are not proportional to one another. So where our diastereotopic protons must give us one proton for each position, they are one structure that is not interconverting. Rotamers can represent two different populations. So they're the whole molecule in two different conformations, and these do not have to be equally favourable, and as a result these peaks can be of different sizes. So this is the room temperature NMR here. And you can see that these are broad. As we heat it up to 55 degrees, we actually start to lose some definition on our rotameric peaks, and this is where we're starting to spin around here just a little bit quicker. And if we spin around that axis fast enough, then we will no longer have axial chirality around that axis, and so these protons would no longer be diastereotopic. However, the T-butyl group, or the Bock group, which was not fast enough to be interconverting to room temperature, at 55 it now rotates quickly enough that you don't see two conformations, instead you see an average. And this is particularly clear in this Bock group here, and I'll just draw your attention to the fact that the peak is not actually situated on either of the peaks above, it is in between, so it's an average of these states.